Today we're going to start with design of finite elements, which is a new code. It used to be design with finite element ME44105, and like everything at the university, you need to have sometimes new codes or whatever. So we expanded the course with 1 point, which is good for you because you get 1 ECTS point extra. And the other nice thing is that we add an extra subject. We do a detailed calculation as well. So it's slightly different from what it is last year, which you get rewarded with an extra point. So for those who want to follow the course of last year, it's basically all the same except for the detailed model, unless you like that, of course. Okay, maybe I'll show you. I introduce myself a bit. I'm Wouter van der Bos. I am here in the faculty. Is better, or is it too dark? The option is on or off. This is that. Okay. Always takes a while. Well, again, I see a lot of faces I've seen before, which is good. That's probably from our section. I'm at the section Transport Technology, which is now connected with the Maritime Technology. And for a lot of you, this is a obligatory course. Some of you might have chosen this because you think it's a nice course. I think so too. But I already warn you, it is, students find this a course where you need to do a lot of work. It might be a bit more extensive. I try to record everything myself. Normally some guy is here and trying to picture me all the time. I'm going to show you how to use the software. I'm going to show you how we are going to do the calculations we have to do. And I also intend to look on your screen and try to record that, so that all the questions you have during the lecture is going to be recorded and put on a collage. So I hope that all that makes life easier for you, because I don't want you to teach and learn you how to use software. I want you to show, okay, what do we need to be able to calculate a structure like a crane or a ship or something large, which is a bit more complex than just check the maximum stresses, and if that's below the yield stress with a safety factor, then it's fine. So if we go to complex structures like ships, cranes, this is a cabin. That's called a ROPS test. If you have a cabin and you want to use that cabin in a heavy machine, one of the requirements is that if you do a rollover test, so you have an accident with your machine, you should survive. So the cabin should remain big enough to hold you inside, and it should also absorb energy. So here you can see complete plastic deformation during the ROPS test, as it's called. This is one of the examples. I teach here since '98. In '99, I started my own consultancy company. Here you see some of the examples. And the software we are going to use is what I started that myself, because I think it is a tool which makes life easier for engineers, and especially makes life easier for students, because I hope that I can show you that we can do much more complex checks on a real system like a crane, and at the same time try to limit the use of software and try to give a better insight in all the checks you need. Yeah. So if you don't agree with that, then my mission is not a thing. Yeah? This is just examples. I don't know. Okay, this is the assignment. What do we have to do? Everybody gets a crane. I got some emails from students who wanted to do something with Formula Student or something else. You can make your own design and do your checks on your own design, but the limitation is that I want to have a structure which is not, I want to see a calculation which is not obvious. Yeah? If it's easier to do by hand, then it's not okay to calculate with finite elements. Because the whole idea of using a software program is that it should help you, not that you do it and just to get your student point, your ECTS points. Yeah? The idea of engineering is if you can do something faster with hand calculations, use hand calculations. Yeah? And if things get too complex, then try to use software. Okay, so what are we going to do? We are going to design a crane. I wanted to make life as easy as possible for you. So I give you a program where you can quickly set up the crane. So I try to avoid that you spend a lot of time in constructing this crane in a completely new software. After that, you have to prove that the structural integrity of the full crane is okay. So I have to check yield. Yeah, all stresses need to be below yield and the safety factor. We have to check local buckling and also global buckling, because if I have some very long legs and I want to be sure that if I send my employee up there that he survives using it. Fatigue is also a problem, since these cranes are in continuous use for a long term, let's say 20 years. So the number of load cycles is typically 4 to 8 million cycles. Yeah, so it's definitely a high cycle fatigue design. And the last one is probably the most important one. If your design is not stable, well, you cannot use it at all. And so also the simple checks you have to do. The idea of a structural engineering is that you have to check everything. Yeah, and you need to check every a location where you might be able to use your crane. You cannot say, well, you can use it in 20 situations, and just the one where we had this accident, well that one was not completely okay, but everything else is fine. So what do you complain about? No, if you get an accident, it's probably, you need to avoid that, so you need to check the complete use, all the possible failure modes, and you need to document that all, and that's what we're going to do. We're going to use the withdrawn Dutch standards, 2018 and 2019. You should use newer crane standards, but since this one is fairly simple, I think it's a better idea that we focus on this one. Yeah, if we go into a newer standards, the basic idea is the same, but it gets over time, it gets more and more complex. Yeah? So in order to save you time, I suggest you use the Dutch standard. If you want to use the FEM standard or the new 30001 standard, be my guest, that's fine. It's not very hard to comply with, but this one is slightly easier, and also I already have the examples for you ready. Okay. If you build a crane, you also need to know, okay, where do we build it for? One of the things is, okay, what do we want to do with a crane? With a ship-to-shore crane, we want to unload containers. Yeah. So the first thing is, what is the size of my ship? And why are these ships the size they have? One of the The names you have for different ships are, here we have Panamax ships, smaller than Panamax, Panamax, post-Panamax, Suezmax, post-Suezmax, and we also have Malaccamax. And why are they called like that? Well, it's obvious. If you have a ship which is bigger than the Panamax Canal, then it doesn't pass there. Yeah, so the ship size was limited, as you can see in the picture. Well, if you make it 2 meters wider, then you cannot go to Panama. So if you want to go from east to west coast of the United States, that is a no-go. Yeah. Same is valid for Suez. If you go from China to Europe, you would like to pass the Suez Canal. Yeah. We happen to have that the Suez Canal has increased in size. The Panama Canal also, but I'm not sure if that's already finished. I thought it was just finished. Anyway, Panamax Canal is not going to be as big as Suezmax, but the Suezmax has been increased to the new biggest standard, which was Malaccamax. Yeah, and why did they use Malaccamax? You can see here, I think the triple E class of Maersk, they were the first. They were thinking, okay, if we increase ship size, the price per container for transport decreases. And as always, it is in Dutch it's called the pig cycle. You have a lot of farmers thinking, hey, the price of pig meat is high, so let's start keeping pigs, and then everybody has pigs, prices drop, farmers get broke, and then the cycle starts over again. Yeah, because if they are all broke, there's nobody producing pigs and everybody still likes pig meat. The same thing is happening with ships. Yeah. We had Maersk introducing triple E class. The competitors also upgraded their ships, and now prices drop to below cost price. So we already have a very big liner in filing for bankruptcy. Yeah, but besides that, the moment these big ships are introduced, all ports need to be able to handle these new ships. So, although this created a lot of big problems for the maritime ship liners, for crane builders this is a blessing, because all the old cranes are not okay anymore. You need to upgrade them or buy new ones. Yeah, and why is it called Malaccamax? I made this picture. You can also check these. These things are very easy to see, but this is a very important street where you would like to pass with your ship. So this is the first extra natural barrier after the Suez and Panamax Canal. Yeah, and the Suez size is now the same as Malacca size. So they increased it back to this one. But it's good to know where these names come from. Okay, the assignment is, depending on the size of the ships you need to handle, you have different size of your cranes. Maybe, I don't know who's in the studio, we have the dispute of Transportkunde. They are going to have to be installed tonight, no? Who's there? Who's doing that? Yeah, you? Okay, maybe it's nice if we can arrange some kind of excursion to, yeah? If it's not for this course, then maybe for the other one. I will, yeah, I think it's, even if you pass this course, I think it's very, if you want to get impressed by size and if you want to build this thing, you need to know how big is big. Yeah? If you have never seen this in port, this is huge. Yeah? Well, if we arrange an excursion, we cannot go up, but this is 60, 70 meters. Yeah, I don't know what the electric engineering building is, but I think that is up till here, not more. Just to give you an idea. And if the boom's up, then you definitely go way beyond that. So let's say this is the building of electric engineering. Yeah, it just gives you an idea of the real size. Yeah? Okay. All these things are always on Blackboard. I try to keep everything up to date. I also have the info of the last lectures. If you, normally the code has changed, so if you want to get info from older lectures, try to use W3416, and you will find there infos and lectures and sheets of last year. I try to keep up. I try to register it. This is new for me. I hope this thing works. I just downloaded the program to have everything recorded. I think it goes with sound. We're going to see this. Yeah. I think recording, it makes life much easier, because especially if I show you something, it seems well, that's simple, and then you try to repeat it yourself and you think, well, how did you do that? Yeah. Okay. I also put a lot of examples of types of cranes. You can look for yourself on internet. This year is also different from the previous years, because before we only had 4 hours lecture and here in the computer room, and there basically, if I explain too much, there's not much time left to help you out. And so we introduced an extra lectures 2 hours on Friday. I'm going to register who is coming there. It's not obligatory to be there, but I think it's a fair deal. If you want to get help from me, then at least you should follow my explanations. Yeah? So if you're not there, I'm not so much willing to help you out. Yeah. The other thing is, if we are here together, it is much easier to ask help from your colleague. How did you do that? Why did you choose this thing? Why is this 60 meters? You can share your ideas. Yeah, I sometimes here it is not allowed that you share and copy the ideas with your colleague. I think it's fine. Yeah, so don't use exact copies. Don't make exactly the same thing. But if you work together and you start with different designs, that's good enough for me. Yeah. Okay. Requirements, I put them in Blackboard. It's always the version of Blackboard is the one which is valid. Yeah. So if I want to update something, because I can see the detailed model which is new for this course. So if that's too complex or too easy, I'm going to add some extra requirements there. But I will notify you. Yeah. On the other hand, if things are not clear, please ask. Okay, this is our course schedule. This week is introduction. As you can see, we always have 2 dates per week. So we have Monday, 4 hours, and then 2 hours on Friday. Should have been easier the other way around, because then I can start 2 hours lecture and then we could immediately start with doing the real work. But it's the way it is. I'm already happy that we are always in the same room and we have 4 continuous hours in the computer room. So there's not much room for complaining here. So what are we going to do? We're going to do introduction today. On Friday, I'm going to explain you the things for the next week. And so that I hope that makes the workflow somewhat better even. And that we can use the computer time we have a bit more in a more efficient way, instead of just listening to me. So basically you can see here the FEM workflow. First we make a model, then we apply the loads. Doesn't want to. Then we do all kind of checks. we're going to upgrade the design a bit, and then we are going to do detailed calculation, and I think that's going to take these 2 weeks. As you can see, there is Christmas in between, so for sure you're going to finish this on time this year. Yep. Okay. Before the coffee break, I want to show you a bit. Okay, what the hell is finite element analysis or FEM technology? Then on what is STC verifier? That is the extra add-on tool I with my company make that myself, and I want to show you why that is a big benefit for you and also for other engineers. And then we are going to a get started example and build the crane model. That's going to be next week. Okay, what is the FEM method, finite element method? You can say, well, you can see it from a mathematical perspective. Instead of infinitely small elements, which work like that, you can get an exact solution. There are a few examples where you can get an exact solution for stresses. I think stresses around the hole. There are some exact formulas to get the real the peak stress, but that is only for maybe 2 or 3 examples where you can get the real stress, which is an exact value. With the use of computers, we are able to use a different method, and that is called finite elements. So, and what is finite? That means that's contrary to infinite elements. Now, infinite is infinitely small, and finite means they have a certain size. And at the beginning, they were pretty big. And there still are, if you make a good model, you can still use reasonable sized elements. But the idea is, if I want to get a stress detail, I need to use more and smaller elements around that zone, and then I get better stresses. Yeah, so that is where finite element method comes from. We use elements where for each element we know how it behaves. Yeah, and if we translate that into mathematics, we do very big matrix calculations. And it just happened to be, it is not that matrix calculations are much easier than hand calculation. It's only a computer is very good in solving this. Yeah? So that's why it is a very nice method. It is not a nice method at all if you want to use this method with hand calculations, because inverting matrices, I think you still had that first year, second year, linear algebra. What was the biggest size? 3x3 matrix? Yeah. How big is the size of a finite element model? Roughly speaking. Let's say we'd make a very coarse model. We use beam elements, yeah? So we are done with 300 elements. Makes, and let's say also 300 nodes, maybe a bit less. How big is my matrix size? You should have had this. I'm not the first one to talk about finite elements. So yeah, maybe some ideas. We have 300 nodes, 300 elements, which determine the matrix size. The elements or the nodes? You can see it here in the equation. We have displacement and a stiffness matrix and a force matrix. Where are displacement and forces on? Elements or nodes? Nodes, exactly. So the number of nodes determines the size of your problem. How many degrees of freedom do we have per node? 6. So 300 nodes times 6 is 1800 by 18. Yeah, so 1800 is the length of this vector and the length of that one. So this one is 1800 times 1800. Not very well suited for a hand calculation. Yeah. Computers, however, are really extremely fast in this, and 1800 by 1800 is, for a computer, considered a very small matrix problem. Now I think up to 1 million elements, so let's say up to 1 million, that is up to 600 or 6 million by 6 million. Matrix size is still doable. And what do you do? Because you need to solve this equation. What does the finite element program do? The only thing it does is it makes, because you want to know the displacements, and you have the force matrix. So you do, okay, you invert the matrix and then you're done. Because this matrix, a vector times a matrix, is a very quick solution. So that's the only thing you do. And you have all kind of tricks to make inverting a matrix quicker. Yeah, but that's good to keep in mind. Okay, this is, well, I'm not going to explain this, but you can revert this into a single matrix, or maybe a matrix with some extra variance of the other matrix. But the idea is always the same. Invert the stuff and then we get the solution. Yeah? There's another approach. You can also say, well, finite elements is just a kind of computer problem and program, and one of the nice things, it gives you pictures with colors. Which is pictures with colors, or, for example, graphs with forces. I think that that approach is not bad either, because one of the nice things of this approach is that you can explain, you can even see these pictures on Discovery Channel, for example. Yeah? So even non-technical students can get the idea of what you want to explain. If you want to see some kind of vibrating object, you can show that with this FEA program. Yeah. So sometimes they used to call this also management porn because it looks so nice. Well, the people now are more used to it, but for a certain while that was definitely wow. That looked cool. Yeah. So that effect is a bit over because everybody knows how this method works. But still, it is one of the biggest advantages that you can make a very complex problem. You can exactly show there it's going. I see here peak stresses here, and I don't have to show a huge list and then say, well, this is a very high number, you see, and then refer this number. And that is that element stress, and then that element, well, that must be somewhere around. Yeah. So the computer graphics are a very, very important part of this method. Another approach is, well, finite element method. It looks like Lego. Here I have a real design, and Lego is cool again, as I noticed since a year or 5. So you have all kinds of people just copying the same thing in Lego. I think FEA models do basically the same, because in the lecture in the other room they do multi-body simulations. You don't know that, but I just, yeah. Iron swap is very interesting too, but it is different. And why is it different? Because with multi-body dynamics you can use bodies which move, and you can make relations between them, and basically you can make any relation as long as it is mathematical possible. Finite elements are completely different. Finite elements are standard elements with default properties, and you need to make a complex structure built on elements which have all the small elements where you can directly understand, okay, what does it do? Yeah, so if I use a beam, I can I can make a mathematical equation that the beam behaves exactly the same as if I would calculate that by hand using a beam element. Yeah. So if you the implication, if I make a beam element model, it has the limitation of a beam element. If I don't want that, I need to use another element. Okay, so I can only go increase complexity if I have the correct, the suitable elements. If I don't have a contact element, it's very hard to make contact. Yeah? I need to trick around. So I need to trick around with Lego parts to make a model which does exactly what I want it to do. Yeah? And if I have done that, then I can see through all these elements what happens. Okay, so the finite element program we use in this course is VMAP. I think most of you used ANSYS before. I don't want to go much in detail. I want to give you a grain model to start with, just to avoid you losing a lot of time in using VMAP. I think it's inevitable to be able to get some idea of how to use it, but my experience is before I used ANSYS, that was much more complex to learn to students. So that's one of the reasons why we use VMAP. The other reason is that my software program currently only works on VMAP. I think we're going to add other programs as well, but for now, no. And I think since I want you to learn to be able to study complex problems and not the simple one, just spend a lot of time building a model and then you get one stress at the stress peak and that's it. No, I want you to do different things. I want you to calculate a real complex model and a complex design where you have to update it according to the findings you find, and these findings are not easy to get. It's a real design problem. Yeah? Since it's called structural design with FEA, you need a tool which gives you detailed information, which is easy also to get. And I hope that works out.